This is an example on how to use Ratey. The reason that we use Ratey is to be able to graph by hand. It's to know how to do everything about the graph without using our calculator. We will use the calculator at the end to verify our solution. So what we want to do is start by using A. A stands for Ratey or stands for roots, so we can write that out here if we need to. And roots are where the numerator equals 0. So we want to set the numerator 3x squared equal to 0 and solve for x. So I divide by 3 and take the square root, and I'm still going to get x is 0. So I know that my root, in this case my only root, is x equals 0. Now A stands for vertical asymptotes and wholes. So remember from rational expressions that to find wholes, we need to see if there's anything that can be simplified. Well, I know that this problem can be rewritten as 3x squared over x plus 2 and x minus 2 because the bottom is a case of dots, difference of two squares. X squared, 4 is really 2 squared. So we take the square root of each of those terms, one gets a positive, one gets a minus sign, and we're done. So nothing is the same on the top and the bottom, so there are no wholes. And now we want to find the vertical asymptotes. So to do that, we set the denominators equal to 0, and we solve, and we get that our vertical asymptotes are at x equals plus or minus 2. So another important information to help me graph. The next one is togetherness. Now for togetherness, the only thing we care about is the bottom, or the numerator. We're looking for special squared terms. So we're looking for something that is all squared, or something that is squared and has nothing out here. Okay? In our case, we don't have any special squared terms on the denominator because we have x squared minus 4. The minus 4 makes it not a special squared term. So in this case, we have no togetherness, which means that the bottom or that the graph will not come together at our vertical asymptotes. And this is important to remember because it's going to help me graph when I get finished. The next thing we care about is the end behavior. We want to know what the graph is doing at the ends of the graph, so what it's doing on either end. So the way we find this is we find the horizontal asymptote. So in this case, we want to look at the degree. And I want to know if the degree is the same on the top and the bottom, if one is higher than the other, depending if it's higher on the top or higher on the bottom. So in this case, I have 3x squared, so a degree of 2 on the top, and x squared, which is a degree of 2 on the bottom. Whenever they're balanced, or they're the same on top and bottom, we simply take the leading coefficient over the leading coefficient, which is 3 over 1. So my horizontal asymptote is 3, because 3 over 1 simplifies to 3. The last thing we need is the y-intercept. And to find the y-intercept, all we're going to do is substitute 0 in for x. So we have y equals 3 times 0 squared over 0 squared minus 4. So I have 3 minus 0 on top, so I have 0 over negative 4, which just simplifies to y is 0 as my y-intercept. So now that I've plotted all these points or figured out what all of this information is, now I should be able to plot a fairly accurate graph. So we're going to start by plotting x equals 0. Now notice that when x is 0 as a root, it's on the x-axis, and y is also 0, those are the same point. In fact, it's going to go straight through the origin. The next thing we're concerned with is our vertical asymptotes. Now, vertical asymptotes are something that we cannot see, so we draw them as imaginary lines because the function is going to get very close to these points, but it is not going to touch it. So we should have a vertical asymptote at -2 and another vertical asymptote at +2. We'll worry about togetherness in a second, but now we also want to plot our horizontal asymptote at y=3. So we're going to go to 3 and we're going to put our y asymptote. So now I know that I've got one point and I've got a whole bunch of imaginary lines that I know my function cannot cross. So the only thing that's really missing here is I don't really know what this point is doing. So I don't know if it's kind of going up here or down here. So sometimes it's helpful to do an additional point. I'm going to check and see what it's doing at x=1. So I'm going to substitute f of 1 into my problem, and I get 3 times 1 squared over 1 squared minus 4. So f of 1 gives me 3 over -3. So I get the point 1, -1. So I'm simply going to plot that point as well. Well, now I can see that this function's going to go down and it's going to get very close to my asymptote, and it's going to do the same on the other side. It's not the prettiest graph, but it'll do. Now we come to the togetherness. The togetherness is going to tell me that since it does not come together at the vertical asymptote, I should not have a graph right here, because then that would be together, but instead I'm going to go up here and follow the asymptotes and get a graph here. Well, notice that we should also have another one here if it was togetherness, but it's not, so it's going to be up here. So this should be a fairly accurate representation of our graph. It's not going to be perfect, but it should be pretty close. So now let's take a look at what the graph looks like using the calculator. So notice that I've put in our function. You can see it right here. Please remember to put parentheses around your numerator and your denominator when you put rational functions in your calculator. And notice that we don't see any asymptotes on the screen. TI-84s do not graph asymptotes. However, if you have a TI-83, it may graph those vertical asymptotes for you. I hope this explains Ratey a little better and gives you a good explanation.